Water is the only resource that cannot be replaced by effort. If your roof leaks, you can patch it. If your firewood runs low, you can cut more. If your food stores are thin, you can hunt or trap or trade. But if your water supply fails, if the well goes dry, if the creek freezes to the bottom, if the pump breaks and the ground is frozen 4 feet deep, and you cannot dig, you have nothing. You cannot make water. You cannot substitute for it. You cannot survive more than 3 days without it, and your livestock cannot survive more than 2. In a frontier settlement dependent on shallow dug wells and surface creeks, a hard freeze that lasted more than a week was not an inconvenience. It was a crisis. And in the mountain valleys of northern New England, hard freezes that lasted more than a week happened every winter. The standard water supply for a Vermont farmstead in the 1880s was a dug well, a hole in the ground 3 to 4 feet in diameter, dug by hand with a shovel and a pickaxe down through the topsoil, the subsoil, the clay, and into the fractured bedrock where groundwater collected in the cracks and seams of the stone. The depth varied with the terrain and the water table. In the valley bottom near the river, wells might reach water at 12 to 15 feet. On the hillsides, 20 to 30 feet or more. The well was lined with dry stacked fieldstone to prevent the walls from caving in, capped with a wooden cover or a stone slab, and fitted with either a rope and bucket arrangement or a hand pump. The problem with dug wells in northern New England was freezing. The frost line in Vermont, the depth to which the ground freezes in a typical winter, ranges from 36 to 48 inches. In a severe winter, the frost can penetrate to 60 inches or more. A shallow well that reaches water at 12 to 15 feet has a water column that begins well below the frost line, but the upper portion of the well, the stone lining, the pump mechanism, the pipe from the pump to the house, is entirely within the frost zone. When the temperature drops below zero and stays there for a week or more, the water in the pump pipe freezes solid. The pump becomes inoperable. The rope and bucket method still works if the well cap can be cleared of ice and snow, but hauling water by bucket from a 20-foot well in sub-zero temperatures, with the rope frozen stiff and the bucket glazing over with ice before it reaches the surface, is brutal labor that produces small quantities of water at enormous cost in time and effort. The deeper problem was that some wells froze entirely. A shallow well in clay soil on a hillside, where the water table dropped in winter as the ground froze and the rain stopped, could go dry by January. The water simply was not there. The well would produce a trickle in November, a seep in December, and nothing at all by mid-January. The family would then depend on hauling water from the river, if the river was still flowing, or from a neighbor's deeper well, or from melting snow, which required enormous quantities of fuel because snow is approximately 90% air, and a bushel of packed snow yields less than a gallon of water. Now, Ioannis Tsakonas did not think about water the way a Vermonter thought about water. A Vermonter looked at water and saw abundance. Rivers, creeks, rain, snow, springs seeping from every hillside. Water was everywhere. The challenge was not finding it, but managing it. Keeping it out of the cellar, draining it from the fields, channeling it away from the foundation. A Vermonter dug a well because that was what you did, and if the well froze or went dry in winter, you dealt with it because that was winter, and winter was hard, and everyone's well froze or went dry, and you got through it. Ioannis looked at water and saw scarcity. He had grown up on the island of Symi in the Dodecanese, a rocky limestone island in the southeastern Aegean Sea, where it rained less than 16 inches per year, and there were no rivers, no creeks, no permanent surface water of any kind. The entire water supply of the island came from two sources: rainwater collected in cisterns and a handful of small springs that seeped from fractures in the limestone bedrock. The springs were precious. They were the only water that flowed year-round, and the villages that controlled the springs controlled the island's survival. Every spring on Symi was captured, not simply used, but captured, the way you would capture an animal. The spring was enclosed in a stone chamber built directly over the seep point, sealed with mortar to prevent contamination and evaporation, and piped through a gravity-fed stone or clay channel to a cistern lower on the hillside where the water was stored for use. The cistern was underground, a stone-lined tank buried in the earth, plastered on the inside with a waterproof lime and volcanic ash morite render that the Greeks had been making since antiquity. The underground location kept the water cool in summer and prevented it from freezing in the rare cold snaps that reached the Aegean. The system was entirely passive. No pumps, no moving parts, no mechanisms that could break. Gravity moved the water from the spring to the cistern. A bucket or a hand pump moved it from the cistern to the surface. The system worked in drought, in storms, in summer heat, and in winter cold because the water was always underground, always protected, always flowing. This was not sophisticated engineering by the standards of Roman aqueducts or Persian qanats, but it was sophisticated engineering by the standards of keeping people alive on a dry rock in the middle of the sea. And Ioannis had grown up watching his father and his uncles maintain the spring capture systems and cisterns that kept the village of Pedi alive through the dry summers when not a drop of rain fell for 4 months and the limestone hillsides turned white as bone in the sun. Ioannis arrived in Vermont in the spring of 1886 with Despina and their 3 children and $22 saved from 4 years of quarry work in Bara, where he had been cutting granite since stepping off the boat from Piraeus. The granite quarries of Bara were filled with immigrant stoneworkers, Italians, Scots, Swedes, and a small number of Greeks, and the work was steady, but the conditions were brutal. The dust from the granite cutting settled in the lungs, and the men who worked the quarries for more than 10 years developed silicosis, a progressive hardening of the lung tissue that made breathing difficult and eventually impossible. Ioannis had watched 2 men from Symi die of it in the Bara boarding house where he lived his first 2 years, and he decided that he would rather farm poor soil in clean air than cut rich stone in poisoned air, and he took his savings and moved his family 30 miles north into the Green Mountain Valley where land was cheap because the soil was thin and rocky and the winters were long and the young people were leaving for the cities and the factories. They bought 40 acres on the west slope of the valley, hillside land that nobody else wanted because the slope was too steep for easy plowing, and the soil was barely 8 inches deep over fractured schist bedrock. But the land had one feature that Ioannis recognized immediately and that no one else in the valley valued: a spring. A seep spring emerging from a fracture in the schist bedrock on the lower slope, about 60 feet above the valley floor and 200 feet uphill from where Ioannis planned to build the house. The spring was small. It produced approximately 2 gallons per minute in spring and summer, dropping to about 3/4 of a gallon per minute in the driest weeks of late August. The neighbors knew about the spring. Harland Bewley, whose farm bordered the Sakonas land to the north, told Ioannis that the spring was unreliable. It slowed to a trickle in August and sometimes stopped altogether in a dry year, and it was too far uphill from the house site to be practical for daily water hauling. Bewley had a dug well 22 feet deep that produced good water 8 months of the year and adequate water for 10, and he considered the well a far superior water source to a hillside seep that you had to climb 200 feet to reach with a bucket. Ioannis listened to Bewley and said nothing. He had learned enough English in the bare quarries to understand the argument, and not enough to explain why the argument was wrong. And in any case, Ioannis was not a man who argued. He was a man who built. The first thing he built was not the house. It was the spring capture. He spent 3 weeks in the summer of 1886 before he laid a single foundation stone for the house, building a stone chamber over the spring seep. He cleared the earth and moss away from the fracture in the bedrock where the water emerged, exposing the bare rock. The seep came from a crack approximately 8 inches long and 2 inches wide, angled slightly downward into the hillside, with water weeping steadily from the opening and running in a thin sheet across the rock face before soaking into the mossy ground below. Most of this water was being lost, absorbed by the soil, evaporated by the sun, dispersed across the hillside in a dozen tiny rivulets that went nowhere useful. Ioannis was going to capture every drop. He built a stone box over the seep, a chamber approximately 4 feet long, 3 feet wide, and 3 feet deep, constructed of flat schist stones mortared together with a lime and sand mixture. The bottom of the chamber was the bedrock itself, and the seep entered the chamber through the crack in the back wall. He mortared every joint carefully, not with the rough field mortar that Vermonters used for dry-laid stone walls, but with the tight waterproof mortar he had learned from the cistern builders on Symi, mixed with fine sand and slaked lime in a ratio of 2 parts sand to 1 part lime, worked until smooth, and applied in thin layers that sealed every pore in the joint. The result was a watertight box that collected the spring water as it emerged from the bedrock and held it in a small pool approximately 18 inches deep at the normal flow rate. From the bottom of the spring chamber, Ioannis laid a pipe. Not a wooden pipe. Wooden pipes were standard in Vermont for short water runs, made from bored-out logs of white pine or hemlock, but a clay pipe. He made the clay pipes himself, from the blue-gray clay that he found in a deposit along the riverbank at the bottom of the valley. He dug the clay, cleaned it of stones and roots, kneaded it with water until it was the consistency of bread dough, and formed it into pipe sections approximately 18 inches long and 4 inches in interior diameter, with a socket and spigot joint at each end so the sections could be fitted together and sealed with mortar. He fired the pipe sections in a pit kiln, a shallow hole in the ground filled with hardwood coals, for 2 days, turning them every few hours to ensure even heating. The fired clay was hard, waterproof, and would not rot, split, or decay in the ground the way wooden pipes eventually did. A wooden board log pipe in wet soil lasted 8 to 15 years before the wood softened and the bore collapsed. A fired clay pipe in the same soil would last centuries. He laid the clay pipe in a trench dug from the spring chamber down the hillside to the house site, a distance of approximately 210 feet with a drop of 60 feet over that distance. The trench was 3 feet deep, below the frost line, and followed the natural contour of the slope in a gentle S-curve that avoided the steepest pitches and the largest boulders. The grade of the pipe was consistent, approximately 1 foot of drop for every 3.5 feet of horizontal run, which gave the water enough velocity to flow freely through the 4-inch pipe without building up pressure that could burst the joints, and enough speed to prevent sediment from settling and clogging the line. This grade was not arbitrary. It was the grade that the cistern builders on Symi used for their gravity-fed lines, developed over centuries of trial and error. Too steep, and the water scoured the pipe and eroded the joints. Too shallow, and the water slowed and deposited silt that eventually blocked the line. 1 in 3.5 was the sweet spot. At the house site, the pipe entered the cellar through the stone foundation wall, passing through a mortared opening that was sealed with a collar of clay and lime to prevent groundwater from leaking in around the pipe. The seal was critical. Groundwater seeping through an unsealed pipe opening would contaminate the cistern with surface water, water that had filtered through soil and manure and decaying leaves and whatever else was on the ground surface, and would defeat the entire purpose of a spring-fed system, which was to deliver clean bedrock-filtered water directly to the house without it ever touching the surface. On Symi, the cistern builders sealed every pipe opening with a 3-layer collar, an inner ring of fired clay pressed tight around the pipe, a middle ring of lime mortar packed into the gap between the clay ring and the foundation stone, and an outer ring of hydraulic lime mixed with crushed terracotta that hardened to a waterproof seal even in wet conditions. Ioannis used the same 3-layer collar technique, substituting crushed brick for the terracotta that was not available in Vermont, but that served the same chemical function. The silica in the crushed brick reacted with the lime to form a calcium silicate compound that was impervious to water. Inside the cellar, the pipe emptied into a cistern, a stone-lined tank built against the foundation wall, 6 feet long, 4 feet wide, and 6 feet deep, holding approximately 1,000 gallons of water when full. The cistern was constructed of the same flat schist stones as the spring chamber, mortared with the same tight lime and sand mixture, and plastered on the interior with a 2-coat lime and sand render that made the walls smooth and watertight. The first coat was a rough scratch coat approximately 1/2 inch thick, applied to the stone and scored with a trowel to provide a key for the second coat. The second coat was a finish coat approximately 1/4 inch thick, made with finer sand and extra lime, troweled smooth until it was as slick as glass. When the 2-coat render cured, a process that took approximately 3 weeks, during which Ioannis kept the surface damp by hanging wet burlap over the walls and misting it with water twice a day, it formed a waterproof shell that could hold water indefinitely without seeping through the joints of the stone behind it. This rendering technique was identical to the technique used in Aegean cisterns for 2,000 years, and it worked because the chemistry of lime and sand render is self-healing. Any micro cracks that develop in the surface are sealed by calcium carbonate deposits from the water itself, a process called autogenous healing that keeps lime-rendered cisterns watertight for centuries. The cistern had a wooden cover to keep out dust and debris and to prevent anyone from falling in, and a copper pipe rising from near the bottom of the tank to a hand pump mounted on a wooden counter in the kitchen above. The copper pipe was the most expensive single component of the system. 6 feet of 1/2 inch drawn copper tubing, purchased from a plumber's supplier in Montpellier for $2.75. Ioannis could have used lead pipe, which was cheaper and more commonly available, but he did not trust lead. On Symi, the old lead water pipes in the village of Panormitis had turned the water sweet-tasting and caused stomach ailments in the children, and the village had replaced them with clay pipes decades before Ioannis was born. He did not know the chemistry of lead poisoning. No one did in 1886, but he knew from village memory that lead and drinking water did not belong together, and he spent the extra dollar for copper. Turned the pump handle, and water rose from the underground cistern through the copper pipe and flowed from the spout into a bucket or a pot or a wash basin, running water in the kitchen, in all seasons, without stepping outside. The pump was a simple cast-iron lift pump, a cylinder with a leather-cupped piston, operated by a handle that moved the piston up and down, drawing water up through the copper pipe on the upstroke and delivering it through the spout on the downstroke. Each stroke of the handle delivered approximately 1 pint of water. 20 strokes filled a gallon jug. The effort required was minimal, less than the effort of wringing out a wet cloth. Despina could fill a 5-gallon wash tub in 2 minutes without breaking a sweat, standing at her kitchen counter in her house slippers while the temperature outside was 20 below zero and the river was frozen solid and Bewley's wife was melting snow on her cook stove a quarter-mile away. If you want to know what happened when an island cistern builder applied centuries of Aegean water engineering to a Vermont farmstead, subscribe to this channel and tell me in the comments where you are watching from. The first winter, 1887 to 88, was mild by Vermont standards. The coldest temperature was -8 degrees Fahrenheit in late January, and the ground froze to a depth of approximately 36 inches. Every dug well in the valley continued to produce water, though several of the shallower ones slowed noticeably in February when the frost penetrated deep enough to partially freeze the upper water column. Bewley's well produced normally all winter. The Tsakona's spring-fed system produced normally all winter. There was no difference to observe, and the neighbors who were aware of the spring system had no reason to think it was superior to a conventional well. The second winter, 1888 to 89, was harder. The temperature dropped to -15 in mid-January and stayed below zero for 9 consecutive days. The ground froze to a depth of 42 inches. 3 shallow wells on the east side of the valley went dry. The water table dropped below the bottom of the wells as the deep frost sealed the surface and cut off the groundwater recharge from rain and snowmelt. The families with dry wells hauled water from the river, breaking through 8 inches of ice to reach the flowing water beneath, and carrying it in buckets up the slope to their homes, a round trip of 15 to 20 minutes for 2 gallons of water. A family of 5 needed 10 to 15 gallons per day for drinking, cooking, and minimal washing. A dairy cow needed 8 to 12 gallons per day. A family with 2 cows and 5 people needed 30 to 40 gallons per day, which meant 10 to 20 trips to the river in sub-zero temperatures. 2 families on the east side lost cattle that winter, not from cold, but from dehydration, because they could not haul enough water from the river to keep the animals alive while also meeting the family's own needs. The Tsakona system produced water without interruption. The spring chamber, buried 3 feet underground, was below the frost line and never froze. The clay pipe, laid 3 feet deep in a trench packed with gravel for drainage, was below the frost line for its entire length and never froze. The cistern in the cellar of the house was protected from freezing by the warmth of the house above and the insulating earth on all sides. The hand pump in the kitchen worked normally. Pump the handle. Water flows from the spout. The total effort required to obtain water was walking to the kitchen counter and moving the pump handle up and down. Despina pumped water for cooking, for washing, for the children's baths, for laundry, for cleaning, all without stepping outside, without carrying a bucket, without breaking ice, without climbing a hill. The spring flow did slow in winter, from approximately 2 gallons per minute in summer to approximately 1 gallon per minute in the coldest weeks of January and February, as the frozen surface reduced the groundwater recharge to the bedrock fracture that fed the spring. But 1 gallon per minute was 60 gallons per hour, 1,400 gallons per day. The family's total daily water consumption, including the 2 cows that Ioannis kept in a small barn beside the house, was approximately 45 gallons. The spring was producing more than 30 times the family's daily need. Even at its winter minimum, the cistern, holding 1,000 gallons, represented more than 20 days of reserve supply, even if the spring stopped flowing entirely, which it never did because the bedrock fracture that fed it was connected to a deep aquifer that was recharged by the entire West Ridge and was not affected by surface freezing. The third winter, 1889 to 90, was the one that changed the valley. January of 1890 brought a cold snap that the old-timers called the worst in 30 years. The temperature dropped to minus 22 degrees Fahrenheit on January 14th and did not rise above zero for 16 consecutive days. The sky was clear and hard and pale blue, the kind of winter sky that means no clouds to hold the Earth's warmth in, and the cold settled into the valley like water filling a bowl. The coldest air pooling on the valley floor where the river ran, the hillside slightly warmer but still brutal, the ridgetops swept by wind that made the effective temperature 30 or 40 degrees below what the thermometer read. The ground froze to an estimated depth of 54 inches, 4.5 feet. This was catastrophic for the wells. The frost did not simply seal the surface and leave the groundwater alone. It penetrated downward through the soil and into the fractured bedrock, freezing the water in the cracks and seams that fed the shallow wells. A well that reached water at 15 feet was drawing from a fractured zone that began at 12 feet. And if the frost reached 4.5 feet, it was freezing the upper portion of that fractured zone and reducing the recharge rate, the speed at which water flowed into the well to replace what was pumped out. A well that could produce 2 gallons per minute in November might produce 1/4 gallon per minute in January, and the family pumping from it would find the well going dry after 10 minutes of pumping and needing an hour to recover before it could be pumped again. Of the 17 operating wells in the valley, 11 failed completely, and 4 more were reduced to a trickle that required an hour of patient hand pumping to produce a single bucket. Only 2 wells continued to function normally. The deepest wells in the valley, both on the valley floor near the river, both reaching water at 30 feet or more, where the temperature of the groundwater remained above freezing year-round. The river froze solid. Not a skin of ice on the surface, frozen solid to the bottom in the shallow riffles, with only a thin trickle of water flowing under the ice in the deepest pools. The ice was thick enough to walk on, thick enough to drive a team of horses across, thick enough that chopping through it to reach flowing water required 20 minutes of hard work with a sharp axe. And even then, the hole froze over again within 2 hours if it was not kept open. Breaking through the ice to reach flowing water now required chopping through 12 to 18 inches of solid ice, and even then the flowing water beneath was barely a trickle, a cup at a time, collected in a bucket held under the ice edge, the water immediately beginning to freeze in the bucket as it was carried up the hill to the house. The buckets developed a crust of ice on the surface before the carrier reached the kitchen door, and by the time the water was poured into a pot on the stove, 1/4 of it had to be chipped out as ice. Several families resorted to melting snow. Despina watched from the kitchen window as the Bewley children hauled sled loads of snow from the field to their house, where Bewley's wife was melting it in every pot and kettle on the cook stove, producing a few gallons of water per hour at the cost of burning firewood that they could not afford to waste. A gallon of water from melted snow required approximately 1 cubic foot of packed snow and 15 minutes of stove time. 40 gallons, a family's daily need with livestock, required 40 cubic feet of snow and 10 hours of continuous stove operation. This was not sustainable. The firewood supply, carefully stacked and measured for a normal winter, was being consumed at twice the expected rate because the stove was running all day melting snow instead of just for cooking and heating. The Sakona's hand pump in the kitchen worked normally. Despina pumped water for the family. She pumped water for the 2 cows. She pumped water for Bewley's wife, who came to the kitchen door on the 3rd day of the freeze with 2 empty buckets and a look on her face that combined embarrassment with desperation. Despina filled both buckets without comment and told her to come back whenever she needed more. Within a week, 4 families were coming to the Sakona's kitchen to fill buckets. Within 2 weeks, when the freeze had not broken and the snow melting was consuming firewood at a rate that threatened to exhaust the winter supply, 7 families were coming daily. Ioannis set a wooden trough outside the kitchen door and ran a pipe from the cistern overflow to the trough so that the livestock from neighboring farms could drink without the families having to carry water in buckets. On the worst days, the trough froze over between uses, and Ioannis had to break the ice crust every few hours, but the water kept flowing because the source was underground, and the underground temperature was 47 degrees year-round, well above freezing, immune to the cold that was destroying the surface water supply of the entire valley. The freeze broke on January 30th after 16 days. The temperature rose to 12 degrees, then 20, then 32. The ice on the river began to crack and shift. The frozen wells began to thaw, though several of the burst pump pipes would not be repairable until spring, when the ground thawed enough to dig. For 16 days, one spring-fed underground system had supplied water to 7 families and their livestock, while every conventional water source in the valley failed. If this story has touched you, share it and subscribe, because the quiet engineering that kept families alive and farms running for generations deserves to be remembered. Bewley came to the Sakona's kitchen on the first day above freezing and sat at the table and drank coffee that Despina made from water that had never stopped flowing, and asked Ioannis how much it would cost to build a spring-fed system for his own property. He did not ask how it worked. He did not ask about the engineering. He had spent 16 days hauling snow and chopping ice, and watching his wife burn through their firewood supply melting snow on the cook stove. And he had lost a calf that was born during the freeze because there was not enough water to keep the mother hydrated during the birth, and the calf died within hours. The loss of the calf was worth approximately $8, not a fortune, but a month's income for a hillside farmer, and a loss that would not have happened if he had had running water in his barn. He was not interested in theory. He was interested in never going through that again. Ioannis told him the truth. Bewley did not have a spring. The West Ridge had several seep springs along its lower slope, but the east side of the valley, where Bewley's farm sat, had no visible spring outcrops. Without a spring, there was nothing to capture. A cistern could be built to collect rainwater and snowmelt from the roof, and Ioannis could build one. But a rainwater cistern in Vermont would not provide year-round water. The collection surface of a typical farmhouse roof was approximately 1,200 square feet, which would capture roughly 700 gallons per inch of rainfall. and Vermont received approximately 36 inches of rain per year, giving a total annual collection of approximately 25,000 gallons. The family's annual water consumption, including livestock, was approximately 16,000 gallons. The arithmetic worked on paper, but the timing did not. The rain fell mostly in spring and summer, and the water was needed mostly in winter. And a cistern large enough to store 6 months of supply would need to hold 8,000 gallons, which would require a tank 12 feet long, 8 feet wide, and 8 feet deep. It was buildable, it was expensive, and it would not solve the winter problem as elegantly as a flowing spring, because a rain cistern is a fixed supply that depletes as you use it, while a spring-fed cistern is a continuously replenished supply that never runs dry as long as the spring flows. Josiah Fenwick, whose farm was on the West Ridge, a quarter-mile south of the Sackenis property, had a spring. It was a larger spring than the Sackenis seep, approximately 3 gallons per minute in summer. But Fenwick had never thought to capture it because his 25-foot dug well had always produced adequate water, and the spring was 250 feet uphill from his house at the top of a rocky pasture that he used for sheep. The spring simply ran down the hillside in a shallow channel, watering the pasture grass and eventually joining the river at the valley bottom. 3 gallons per minute, 4,300 gallons per day, 1.5 million gallons per year, running untouched down the hillside and into the river, while Fenwick's family hauled water from a well that froze every hard winter. Ioannis built Fenwick's spring capture system in the fall of 1890, working 4 weeks between the end of harvest and the first hard frost. He began, as he always did, with the spring chamber. Fenwick's spring was larger than the Sackenis seep. It emerged from a wider fracture in the bedrock, approximately 14 inches long and 3 inches wide, with water flowing steadily rather than weeping. The higher flow rate meant a larger chamber was needed to contain the water without backing up and overflowing. Ioannis built the Fenwick chamber 5 feet long, 4 feet wide, and 3 feet deep, roughly double the volume of his own chamber, with a mortared overflow notch at the top of one wall that would redirect excess water safely down the hillside if the chamber ever filled beyond capacity. This overflow was a safety feature that Ioannis had learned from his father. If the downstream pipe ever became blocked by sediment or ice or a tree root, the water in the chamber would rise until it reached the overflow notch and then spill harmlessly down the surface instead of building pressure against the chamber walls and eventually bursting the mortar joints. A spring that could not be stopped had to be given somewhere safe to go when the normal path was blocked. The clay pipe for the Fenwick system required 32 sections, 2 more than the Sackenis system due to the longer distance. Ioannis made the pipes over 2 weeks in September, forming them on a flat board beside the river, drying them in the sun for 4 days, and firing them in the pit kiln for 2 days each batch. He could fire 6 sections at a time in the kiln, so the 32 sections required 6 firing sessions over 12 days. Each firing consumed approximately half a cord of hardwood, oak, and maple splits that burned hot and steady for the 2 days needed to bring the clay to full vitrification temperature. The total fuel cost for firing was approximately 3 cords of hardwood, which Ioannis cut from Fenwick's own woodlot. Fenwick helped with the cutting and the kiln tending, and Ioannis showed him how to judge the firing temperature by the color of the clay. Blue-gray when raw, dark red when half fired, pale brick red when fully fired and ready to cool. Fenwick was fascinated by the process in the way that a man who has worked with wood all his life is fascinated when he first sees what fire can do to clay, transforming a soft material that dissolves in rain into a hard material that water cannot penetrate. The trench from the Fenwick Spring to the Fenwick House was dug by both men working together over 8 days, Fenwick on the pickaxe breaking through the rocky soil, and Ioannis on the shovel clearing the loose material and shaping the trench bottom to the correct grade. The total distance was 250 feet, with a drop of 75 feet, a steeper grade than the Sakonis system, approximately 1 foot of drop for every 3 1/3 feet of horizontal run. The steeper grade meant faster water velocity in the pipe, which was an advantage for preventing sediment accumulation, but required extra care at the joints, where the increased pressure from the faster-moving water could work mortar loose over time if the joints were not sealed with extra thickness. Ioannis applied double mortar at every joint on the Fenwick system, a full inch of mortar around each socket and spigot connection instead of the half-inch that was standard, and he let each joint cure for 24 hours before backfilling the trench, giving the mortar time to set hard before the weight of the gravel and earth was placed on top. The cistern in the Fenwick cellar was built to the same specifications as the Sakonis cistern, 1,000 gallons, mortared schist stone, 2-coat lime render, and Ioannis installed the same 3-layer pipe collar at the foundation wall entry, the same copper pipe to the kitchen, and the same model of cast iron hand pump. The Fenwick system was operational by the 3rd week of October 1890, 3 weeks before the first hard frost. Even this single system transformed the Fenwick household. The kitchen had running water for the first time. Fenwick's wife, Dinah, who had hauled water from the well in buckets for 19 years, 2 trips per day in summer, 3 in winter when the pump was stiff and the yield was low, now pumped water at her kitchen counter while standing on a dry floor in her house shoes. She told Despina that the hand pump had changed her life more than any other single object she had ever owned, including the cook stove, because the cook stove only changed how she cooked, but the hand pump changed everything. How she washed, how she cleaned, how she bathed the children, how she did laundry, how she preserved food, how she cared for the sick. Water touched every task in the household, and having it flow from a pump at the kitchen counter instead of arriving in buckets from a well 100 feet away meant that every task that required water was faster, easier, and less exhausting. Fenwick's firewood consumption dropped noticeably that winter, not because the spring system provided heat, but because Dinah was no longer burning firewood to melt snow during the cold snaps when the well froze. The savings were approximately half a cord per winter, $3 worth of wood, which did not sound like much, but which accumulated year after year, and which represented hours of cutting labor that Fenwick could spend on other farm work. The total cost of the Fenwick system was $42, $18 in materials, clay pipe sections, lime, copper pipe, pump hardware, and miscellaneous fittings, and $24 in labor, 4 weeks at $6 per week, which was the going rate for skilled masonry work in the valley. This was more than the cost of digging a new well, which typically ran $20 to $30 for a 20-foot well, including the stone lining and pump. But the well would freeze. The spring system would not. There was also the matter of water quality, which nobody in the valley discussed openly, but which affected every family. A conventional dug well in the valley was a hole in the ground, 15 to 25 feet deep, lined with dry stacked fieldstone that allowed groundwater to seep through the joints and fill the well from the sides. This meant the well water was surface water, water that had percolated down through the topsoil, past the outhouse, past the barnyard, past the manure pile, past whatever dead animals or rotting vegetation happened to be decomposing in the vicinity, and into the well through the same permeable stone joints that allowed groundwater in. The connection between contaminated well water and illness was not well understood in the 1880s. Germ theory was still new, and the specific mechanisms by which waterborne pathogens caused typhoid, cholera, and dysentery were not yet part of common knowledge. But the correlation was observed, even if it was not explained. Families whose wells were close to their outhouses had more sick days than families whose wells were uphill and far from contamination sources. The Sakanas spring water, by contrast, was bedrock water, water that had filtered through hundreds of feet of fractured schist, traveling slowly through cracks and fissures in the rock for years or decades before emerging at the spring seep. This deep filtration removed virtually all organic contamination, all surface pathogens, all the biological material that made shallow well water a health hazard. The spring water was as clean as any water source available in the 19th century, short of boiling, and it arrived at the kitchen pump without ever having touched the surface. In the 10 years following the installation of the Sakanas spring system, not a single member of the Sakanas family contracted the stomach complaints and intestinal fevers that periodically swept through the valley, while families drinking from shallow wells lost days and sometimes weeks to illness every year. Despina attributed this to clean living. Ioannis attributed it to clean water. Both were correct, but the water was the more important factor. The well would need its pump repaired or replaced every 3 to 5 years as the leather gaskets wore out and the cast iron cylinder corroded. The spring system's clay pipe and stone cistern would need no maintenance at all. The clay pipe was inert and would not corrode, and the mortared stone cistern, sealed with lime render, would hold water indefinitely without repair. The only wearing component was the kitchen hand pump, which was the same pump used on a conventional well and would need the same maintenance regardless of the water source. Over 20 years, the well would cost approximately $40 in repairs and replacements. The spring system would cost approximately $0 in repairs. The spring system was cheaper over time, more reliable in winter, and produced better water. Spring water filtered through bedrock was cleaner and clearer than groundwater from a shallow dug well, which was subject to contamination from surface runoff, animal waste, and the outhouse that was typically located within 50 feet of the well. The winter of 1890 to 91 was moderate, and both the Sakanas and Fenwick systems performed without issue, while several wells in the valley froze again in a 10-day cold snap in February. The winter of 1891 to 92 was severe, minus 18 degrees for 11 days in January, and 8 wells failed. The Sakanas and Fenwick systems produced water continuously. Fenwick told everyone who would listen that the spring system was the best investment he had ever made, and he told them with the fervor of a man who had spent the previous 2 winters melting snow on his cook stove and watching his cattle suffer. By 1895, Ioannis had built spring capture systems for 5 families in the valley, every family that had a spring on their property. He had also built 3 rainwater cisterns for families without springs, collecting roof runoff through clay gutters into underground stone tanks. The rainwater cisterns were not as reliable as the spring-fed systems. They could not provide unlimited water in a prolonged freeze because the supply was finite. But they provided a reserve of 1,000 to 1,500 gallons that could sustain a family through 2 to 3 weeks of frozen wells, which was long enough to survive the worst cold snaps. The total cost of all 8 systems was approximately $350. The total water security they provided was absolute. During the severe winter of 1895 to 96, when the temperature dropped to minus 25 degrees and 17 wells froze or failed, the 8 Tsakonas-built systems produced water without interruption, supplying not only the 8 families but their neighbors as well, just as the original Tsakonas system had done in the freeze of 1890. The pattern repeated every severe winter. The wells failed, the river froze, the families without underground systems hauled snow and chopped ice, and the families with Tsakonas systems pumped water from their kitchen counters as though it were a summer afternoon. Eleni, the oldest Tsakonas daughter, who was 11 when the family arrived in the valley and who had helped her father dig the trench and lay the clay pipe for the original system, later told the story to her own children with a detail that Ioannis himself never mentioned. When he finished the spring chamber, when the last stone was mortared and the last joint sealed and the water was rising in the stone box clear and cold, he stood up and looked at the chamber for a long time and said nothing, and then walked down the hill to the house site and began digging the trench. He did not celebrate. He did not explain what he had built or why. He did not tell anyone in the valley what the chamber was for, or how the pipe worked, or why he had spent 3 weeks building a water system before he had a house to put it in. The water was captured. The work continued. By 1897, the economics of the spring-fed system were clear to everyone in the valley. The 5 spring-fed systems had been in operation for 4 to 10 years. Total maintenance cost across all 5 systems, $0. Total system failures, 0. Total days without water, 0. The conventional wells in the valley, by contrast, had collectively failed 43 times during the same period, an average of approximately 2 failures per well per decade, each failure lasting 5 to 16 days, each failure costing the family in lost livestock productivity, in firewood burned to melt snow, in labor hours spent hauling water from the river or from a neighbor. The cost of each failure was difficult to calculate precisely, but the families estimated it at $10 to $20 per event in lost productivity and emergency measures. Over a decade, the conventional well cost its owner approximately $30 to $40 in failure-related losses, plus $20 to $30 in routine maintenance and repair, a total cost of ownership of $50 to $70 per decade. The spring-fed system cost its owner $42 once and $0 thereafter. The break-even point was the first severe winter. Ioannis built his last spring system in 1903 for a family named Stavros, a Greek family newly arrived from the island of Kalymnos, who had settled on the West Ridge and who sought out Ioannis specifically because they knew, as any islander would know, that the spring on their property was not a nuisance seep to be ignored, but a treasure to be captured and kept. Stavros had been a sponge diver on Kalymnos, a dangerous profession that had given him strong lungs and a deep familiarity with water in all its forms. And when he saw the seep spring on his new land, he immediately asked in the valley who could build a cistern, and every person he asked pointed him to Ioannis. The Stavros system was the most ambitious Ioannis had built. The spring was 300 feet from the house site. The terrain was steeper and the bedrock was harder schist that required a day of chiseling to create a flat foundation for the spring chamber. But the system worked as well as every other system Ioannis had built, because the physics was the same, and the technique was the same, and the materials were the same, and water does not care whether the pipe is 200 feet or 300 feet long as gravity has a path to follow. After 1903, the requests slowed. The younger generation was drilling deep wells, machine-drilled wells that reached 40, 60, 80 feet into the bedrock, penetrating below the permanent water table where the water never froze and never failed. Deep-drilled wells were expensive, $100 or more for the drilling alone, plus the cost of a casing pipe, a pump, and the connecting plumbing to the house. But they were reliable in all seasons and did not require a spring on the property, and they represented the modern approach to water supply that was replacing the hand-dug well across rural New England. The drilled well was a brute force solution. Drive a steel pipe deep enough into the earth, and you will hit water that never freezes and never runs dry, regardless of the surface conditions. It required no knowledge of springs, no understanding of aquifers, no skill in laying clay pipe or mortaring stone. It required a drilling rig and a checkbook. The spring capture system was an elegant solution. Use gravity and the natural flow of bedrock water to deliver a continuous supply to the house with zero mechanical components and zero ongoing cost. It required knowledge, skill, and a spring. In a world where drilling rigs were becoming available and checkbooks were easier to come by than knowledge, the elegant solution lost to the brute force solution, as it usually does. The spring-fed systems that Ioannis had built continued to operate. The clay pipes did not corrode. The stone cisterns did not leak. The mortared spring chambers held their seal decade after decade, the water flowing continuously from the bedrock fracture through the pipe and into the cistern, gravity doing the work that pumps and machinery did for everyone else. The Sakonas system, the original, built in the summer of 1886, was still producing water 50 years later when Ioannis's grandson was farming the same 40 acres. The clay pipe that Ioannis had formed by hand from riverbank clay and fired in a pit kiln was still intact, every joint still sealed, every section still round and clear, the interior surface smooth and free of mineral deposits because the spring water was low in dissolved minerals and slightly acidic from filtering through the schist bedrock. The stone cistern still held 1,000 gallons. The lime render on the interior walls was as smooth and waterproof as the day it was applied, the autogenous healing process having sealed every microcrack that had formed over 5 decades of use. The spring still flowed. It flowed in the summer heat and in the winter cold. It flowed during the drought of 1911 when the river dropped to a trickle, and 3 drilled wells went dry because the water table dropped below their reach. It flowed during the freeze of 1918 when the temperature dropped to -26 and the entire valley was locked in ice for 3 weeks. It flowed because it had always flowed, because the bedrock fracture that fed it was connected to an aquifer that was recharged by the entire West Ridge. An aquifer that held millions of gallons of water in the cracks and fissures and porous zones of the schist, and no single winter, no single drought, no single year of unusual weather could deplete it. 50 years, 0 maintenance, 0 failures, 0 days without water, from a spring that Harlan Bewley had called unreliable and a system that nobody in the valley had seen before, built by a man from a dry island in the Aegean who understood something that the people surrounded by rivers and rain and snow had never needed to learn, that water is not a problem to be managed. It is a gift to be captured and held and carefully protected from the cold that would take it away. And once captured, enclosed in stone, sealed with mortar, piped through clay, stored underground where no frost can reach it and no drought can diminish it, it becomes the one resource that never fails, the one supply that outlasts every winter, the one certainty in a landscape of uncertainty. No myths, no miracles, just stone, clay, gravity, and the patience of water that finds its way underground.